This presentation is delivered by the Stanford Center for Professional Development.
All right, so today we're going to the Alps.
An innovative space rover with extended climbing abilities. Switzerland.
Autonomous mobile robots have become a key technology for unmanned planetary missions. To cope with the rough terrain encountered on most of the planets of interest, new locomotion concepts for rovers and micro-rovers have to be developed and investigated. In this video sequence, we present an innovative off-road rover able to passively overcome unstructured obstacles of up to 2 times its wheel diameter. Using a rhombus configuration, this rover has 1 wheel mounted on a fork in the front, 1 wheel in the rear, and 2 bogies on each side. Here we can see the trajectory of the front wheel mounted on the fork. An instantaneous center of rotation situated under the wheel axis is helpful to get on obstacles. To ensure good adaptability of the bogie, it's necessary to set the pivot as low as possible whilst simultaneously maintaining maximum ground clearance. This architecture provides a non-hyperstatic configuration allowing the bogie to adapt passively to the terrain profile. Motion in structured environments. For climbing stairs, it's necessary to have a good correlation between bogie size and step dimensions. We can see that the rover is able to climb regular stairs effortlessly. Motion in an unstructured environment. We also made some outdoor tests on rocky terrain. As can be seen, the rover demonstrates excellent stability on rough terrain. It advances despite a lateral or frontal inclination of 40 degrees and is able to overcome obstacles like rocks even with a single bogie. In a next step, the robot will be equipped with adequate sensors for fully autonomous operation.
So it's quite interesting because when we think about wheeled robots, we think about mobile platforms working in indoor environments, and it's really difficult to imagine these machines going around and being able to go over obstacles. So we usually try to use, what do we use in uneven terrain? I mean, what would be the solution, the other solution, the alternative solution? Legged. So we always think legged locomotion would be the solution, and in fact legged locomotion is very adapted to those problems because now you can move each leg and go over obstacles. But in here we can see a way that you in fact putting that compliance inside the structure and moving the structure as you are adapting to the environment. So this is really a quite nice solution. But there was also design that combines legged locomotion together with wheeled locomotion. So you have a hybrid solution where you are using the wheels and pushing with the legs. So there are several ways of even going further beyond just modifying the chassis itself, going to adding some propulsion by the legs. So in fact this project was pursued further, and I'm not sure if we will have more videos on this one. Okay, so let's go back to dynamics, and I think today we will finish that portion of the lecture. I think I emphasize dynamics. I also emphasize the fact that dynamics is very, very closely related to control, and we really need to understand those equations of motion in order to be able to control well the robot. So let's go back a little bit to what we saw on Monday about the Lagrange equations. We saw that we can describe the dynamic behavior of the robot, that is its motion. It's as a function of the torques applied to the robot through this Lagrangian equation that involves the kinetic energy and the potential energy. So K is the kinetic energy and U is the potential energy. And we saw that because our potential energy is only function of the configuration, we can separate this equation and find the structure related to the inertial forces and the forces applied to the robot, that is the gravity and the torques, which means that we can write the equation, put the inertial forces on one side, and then analyze the dynamics, that is the inertial forces dynamics, and then see the effect of those forces applied to the system, that is the external torques through the motors. At each joint we have a motor, and the motor is applying a torque at the joint or a force at a prismatic joint, and also the effect of the gravity that are coming. So if we analyze this equation, we saw that we can write it in this form, in the form of a mass matrix multiplied by the acceleration at all the joints, plus some additional forces that are function of the velocity and function of the fact that the mass matrix is configuration dependent. And those forces could be obtained if we express our kinetic energy in its quadratic form expression, that is 1/2 q dot transpose m function of the configuration q dot. This is a scalar, and if we do the derivation of this scalar, we find in fact that we have this equation, that is this part will brings those elements, the mass matrix, the acceleration, and this part which represent the centrifugal Coriolis forces. And we can see from this expression that when q dot is equal to 0, this will disappear, or if the mass matrix was constant, this will also disappear. So we saw the proof of this, I think that you remember. So in this form, the equation now can be written in terms of the mass matrix, the derivative of the mass matrix and the velocities, and the gravity forces equal to the applied torques. Because the mass matrix is this quadratic form, now we can, if we are able to extract the kinetic energy from our analysis of the different motions of the links, we should be able to find the mass matrix directly from the kinetic energy. Then we put it there, and because V is solely function of the mass matrix and the velocities, we should be able to obtain V, and that will give us the full equation simply by computing the kinetic energy. Okay? So that's what we're going to do. We're going to do this analysis and find how we can find the mass matrix. And once we found the mass matrix, we will find V. And then G is a piece of cake. Okay, so how are we going to proceed? So here is an example of an arm. And we are looking at one of the joint, one of the links, link I. So this is a rigid body, and this rigid body has a mass distribution, has some inertia, and has some mass. So what we're going to do, we're going to look at this kinetic energy associated with that specific link. And the idea is, if we are able to describe and find this kinetic energy, we will be able then to go over all the different links and do the sum and find the total kinetic energy. And because we have this relation, we can put the two together and we can then identify the total kinetic energy from the individual kinetic energies. So for link I, the total kinetic energy is going to be the sum of the different kinetic energies. So link I will be here, and when we walk through all the links, we are going to find different kinetic energies that we can sum and find the total kinetic energy. But then we will say the kinetic energy of the system should be expressed as a quadratic form on the generalized velocities. And the question is, how can we then do this identification and extract M? So you see the algorithm? Just doing this part and then identifying M from that sum. All right, so I'm sure half of you remember the kinetic energy and the other half does not remember. So how we define the kinetic energy? Those of you who remember. So you have a rigid body at rest, and we move it to some velocity v. What is the kinetic energy? Yes?
1/mv squared.
Yeah, but what does that represent?
It's a work you need to move from rest to velocity v.
Yeah, I think I understood what you mean, but could you repeat it clearly so everyone can?
So it's a work needed to move the particle from velocity 0 to...
From rest to its current state. Yes, that's the definition. So it's the work done by the external forces to bring the system to its state from rest. And that means we are going to take a look at this point mass and its final velocity, v, and that work will come to be 1/2 mv squared. Now, this is for a point mass, but we are working with links. And links are rigid objects, right? And they have rotational motion, and which means each of the particle is moving at different velocity, etc. And there is a quantity that allow us to evaluate that inertial forces generated by those particles. And this is the inertia. So the inertia of the rigid object is going to intervene now if we look at rotational motion. So the kinetic energy associated with a rigid body whose inertia is IC, C here represent the inertia computed with respect to the center of mass, as we have everything is represented at the center of mass, will take this rigid object from rest, the zero kinetic energy. When we reach omega, there will be some kinetic energy, and this kinetic energy is going to be you. What half?
Omega transpose in the inertial.
Inertia. Omega. So if this was just 1 degree of freedom, this would be basically a scalar I representing the inertia about that axis, omega squared. But we are looking here at a spatial motion, so I is a matrix and the omega is a vector, so we need to write it in this form. Okay? So if we take this rigid body and put to it together V and omega, that is, it is undergoing both angular motion or rotational motion plus linear motion, then the two will combine, and the total kinetic energy will be the sum of these two kinetic energies. Okay? We're clear about this. Is very important. Once you understood the kinetic energy, you have all the dynamics. The rest is just math, basically. So you understand this for one rigid body? Good. Then we're going to be ready. We just write this. All right. Now pay attention. From here, we're going to find the dynamic equations of a multi-body articulated system directly by summing these ki's. If you understand this, you will see immediately that M is going to emerge this mass matrix for all the structure. So the kinetic energy of one link is this sum, combining the kinetic energy associated with linear motion and the kinetic energy associated with angular motion. And let's do the sum. So the total kinetic energy is this sum, and I'm going to write it. Just to remind you, we have selected for this structure, we selected a set of generalized coordinates, Q. And that means we have a set of generalized velocities, Q dots. So these are the minimal number of parameters or configuration parameters needed to represent this configuration. Once Q is defined, the configuration is locked, right? So now we can say, because we know these generalized coordinates and generalized velocities, we can say the kinetic energy is also this expression of half Q dot transpose M Q dot, where M is this positive definite, symmetric positive definite matrix that appears in this quadratic form. So we have these two different ways. The first one is here. We are saying we can compute individually the kinetic energies without worrying about the